All right, so today we're going to look at arithmetic sequences and series. And the nice thing is, you guys have worked with these before, at least to some extent. Now let's kind of try to jog our memories a little bit. What is it that makes a sequence arithmetic? Remember, Neve?
It has the same difference between every number.
Very good. It has the same difference between every number. So like the one that we did yesterday, or the other day, where we were doing 2, 4, 6, 8, 10, and so on. There's a difference of 2 between all of those numbers. Now it doesn't have to be something nice and simple like 2. It could be anything, all right? We could have 2, and then 2 plus the square root of 3, and then 2 plus 2 times the square root of 3, and then 2 plus 3 times the square root of 3, and so on. Every one of those has a difference of the square root of 3. We're just adding one more on every time. That would still be an arithmetic sequence, okay? Because there's a common difference, all right? It's really what makes the key. There is a common difference. Now, I've given you an arithmetic sequence here. A sub n equals 2n plus 4. Remember, we said when we're defining any sequence, you give an equation. A sub n equals something. All right? So here I've given you one. A sub n equals 2n plus 4, and I'm telling you this is arithmetic. So let's go ahead and first of all find the first 5 terms of this. And I want you to try to sketch the graph of it as well. Okay, so take a moment here and try to figure that out. Alright, so let's think through these terms here. Okay, what do we get for a sub 1? 6, alright. Now if I'm going to graph that, what point is that going to be?
1, 6.
1, 6. Good. The n is like our x coordinate, it's our independent variable. The a sub n is the dependent variable, so it's like our y. So I have the point 1, 6. Okay? A sub 2 is
8.
8. Okay? So 2, 8. How about a sub 3?
10.
Good. So we have the point 3, 10. A sub 4?
12.
Good. 12, 4, 12. And a sub 5?
14.
14. Okay, so a sub 5 is 14. Now, we have it all plotted out there. We have our different terms. What is our common difference in this case? We often use the letter D to represent common difference. If you remember, what would it be in this case?
Plus 2.
Yeah, plus 2, okay? It's changing by 2 every time. Now, this is the number one thing I want you to get out of this whole day. Because if you can make this connection in your head, everything to do with arithmetic sequences will be very, very easy. Okay? As you look at this and you look at it graphed, what do you notice? It's increasing, it's linear. Okay? It's linear. Now, we're not going to sketch a line through the points because this is a sequence. It's not defined for fractional values of n. Okay? But it is linear, and because of that, we can figure out everything to do with the sequence using stuff we know about linear functions. Okay? For example, notice the definition of the sequence itself. What does it look like?
MX plus B.
Yeah, it looks like y equals mx plus b, doesn't it? Or ax plus b if you're used to using that. But it's slope-intercept form, okay? So just looking at the definition of a sequence, you can actually tell if it's arithmetic. Ask yourself, does that look like the equation of a line? Okay? Also, notice the common difference. Okay? When we were working with lines, what was that feature of a line that told us what our common difference or our rate of change was? Slope. Okay? So guess what? If you need to find a common difference, really, you're looking for slope. Okay? You're looking for slope. If you can get that into your head, then everything else is easy because you've been working with lines since, pre-algebra or even earlier than that. Okay? You guys know how to use 2 points to find the equation of a line. So let's look at how we would do this, all right? Let's say that we are given a sequence of numbers and we're asked to find its definition. Right? The first thing, of course, that we should ask is it arithmetic? So what are we looking for to determine arithmetic? A common difference. Do the numbers go up by the same amount every time? Is there a common difference? Okay, is there a common difference? By the way, am I writing large enough? Is it okay?
Yeah.
Okay, I'm trying to write a little bigger than I had been. The next thing you need to ask yourself is, what is that common difference? Okay? And we just related common difference to what else? Slope, alright? So really you're looking for the slope. Now, the one difference here between when you're just working with lines and when you're working with a sequence is that you always need to get your slope as something over 1, okay? Because you want the common difference for every one step. So if you got 3 halves, it's going to go up 3 every 2 parts of the sequence. So you need to recognize it would be 3 halves of a unit every 1 step of the sequence. So your common difference would be 3 halves. It's a fine difference there, but just something to be aware of, okay? Then you would need to find a sub n, okay? Now, I list this right here, okay? There are a couple formulas that your textbook will give us. However, if you remember how to find equations of lines, you don't need to memorize any new formulas, okay? Let's think about this formula 3, 6, 9, 12, 15, 18. Okay? First of all, is it arithmetic?
Yes.
Yes. What's our common difference?
3.
3. Okay? So D is 3. Now, if you think about these in terms of points, like the ones we graphed on the previous example, what's a point on this linear relationship?
1, 3.
1, 3. Yeah, the first term, since a sub 1 equals 3, that gives us a point 1, 3 if we were to graph it. So now that we know the slope and we know a point, how do we find the equation? Okay, you can use y equals mx plus b, or you can use point slope form. Either one you're more comfortable, I don't care. Okay. The key is, though, that instead of y's, you're using a sub n's. So it's going to be a sub n minus the y coordinate equals your slope, or common difference in this case, times n minus the x coordinate, which is 1. I'm using the point slope form. Okay? Now, you can't leave it like that,
Yeah.
but
Can't you just add 3 to both sides?
yeah, we would add 3 to both sides. So a sub n is, if I distribute that, it's 3n minus 3 plus the 3, so those actually cancel out to 0. So my final definition for this sequence is a sub n equals 3n.
Wait, can you do it with the other one, why everyone else is good?
Yeah, in that case, if you were doing it that way, you would have a sub n equals 3n plus b, if you want to use like slope intercept form.
Mm-hmm.
So then you would plug in the 1 for n, and you'd plug in the 3 for a sub n, and then you would find that, oh, b equals 0. So you'd have to go back and plug it in. A sub n is 3n plus 0. Okay. You'll get it either way, so just use whichever method you're more comfortable with. How about the second sequence here?
There's no common difference.
No, the common difference, there isn't one. It keeps going up. You know, we've got 3, and then 4, and then 5, 6. There actually is a way. Notice how the differences have a common difference. There is a way to do a quadratic one. We're not going to mess with those this year. If you've done it in the past, that's great. But we're not going to mess with those at this point. So we would just leave that. That's not an arithmetic sequence. Okay. The next one, however, does go up by how much each time? Yeah, 1.5. So d equals 1.5. All right. So try to figure out what a sub n would equal for this one. Take a minute here. Try to figure that out. So if we know it's a sub n equals 1.5 n plus something, we just have to figure out what that something is, right? So what point did you guys use?
The first one.
1, 3 would work. You could use 2, 4.5. You could use 3, 6. All right? It doesn't matter which one you use as long as you just pick one of the points that you know. Okay, 1, 3, 2, 4.5, 3, 6, 4, 7.5. Any of these. If you know the first one, you might as well use it because ones are easy to work with. So we know a sub n minus 3 is going to be 1.5 times n minus 1. Okay? So a sub n minus 3 is 1.5 n minus 1.5. If you add 3, you have 1.5 n plus 1.5. Okay? And that would be the definition of that sequence. Okay? Does anyone have any questions about this before we move on? Or does that make sense? Do we understand?
Yeah.
Okay. Alright, so let's talk about partial sums. This is a term we ran into yesterday. Okay? If I ask you to find the fifth partial sum, what am I asking you to do?
To add up the first 5 equations.
Yeah, find the first 5 terms and add them all up. Okay? So for the one that we found that was the first one, 3, 6, 9, and so on, we would do 3 plus 6 plus 9 plus 12 plus 15. Okay? And we'd add up all those and we would get 45. Okay? If we did the second one, you know, we had 3, 4.5, and then 6, and then 7.5, and then 9. You add all those up and you'd end up with 30. Okay? Now, with 5 terms, that wasn't too bad. But what if I had asked you to find the 100th partial sum? Okay, that could take a while. So, because this is arithmetic, there actually is a little bit of a pattern here. It's really kind of a cool pattern. Notice what happens. Let me change colors here. Notice what happens if I were to take the first term and pair that up with the last term. Okay? And then I took the next term and I paired it up with the next to the last term. What do you notice here? They're the same. They both add up to 18, right? Now 9 doesn't have anything to pair it with, but what do you notice about 9?
Adds to 18 with 9, like 9 plus 9 is 18.
Okay, yeah, it's half of that 18, right? Well, let's look at this other one. 3 plus 9 is 12. What's 4.5 plus 7.5? 12, and 6 is half of 12. There's a pattern here. If we had an even number of things, the middle two would pair up to the same sum as everything else. Okay? What we see here is actually going to give us this formula that we see down at the bottom. The sum of a finite arithmetic sequence with n terms is given by this formula. So the partial sum that we were finding here was S sub 5. We use the capital S for sum, and it's the 5th partial sum. Alright, so we use S sub 5. Now, if you notice the formula, this is saying that you would add the first term and the last term, just like we did. We added 3 and 15 and 6 and 12 and so on. We started by adding that first term and the last term, and then basically it's saying you're going to have n divided by 2 pairs. Alright? So if we had 5 terms to start with, we got 2.5, because remember 9 was half of 18, we got 2.5 pairs. Okay? That's how that works. Okay? Now, this formula was actually derived, I don't know if he was the original one to derive it, but there's a famous mathematician by the name of Carl Friedrich Gauss. He's an amazing mathematician, did a lot of stuff in a lot of different mathematical fields. But he actually figured this out and saw this pattern when he was in elementary school. Just kind of amazing. His teacher gave him the task, and the rest of the class, the task of finding the sum of all the numbers from 1 to 100. Yep. And he didn't feel like doing the task that he was really assigned to do, because that's a lot of numbers to add together. So he started looking at them and he noticed a pattern. If you put the 1 with the 100, you get 101. And if you put the 2 with the 99, you get 101. And if you keep doing that, how many pairs are you going to end up with that add up to 101?
So 49. 51.
Here, 49, 50, or 51. What is it?
49. Once you get to 50, you can't add 50 to 50. There's only 50.
Well, but you add 50 to 51, right?
Oh yeah.
So we actually do end up with 50 pairs, and all of those pairs add up to 101. So guess what? Whoop, not 100. 101. So the numbers 1 through 100 add up to 5,050. Okay? So he figured that out in a couple of minutes, went up and tossed his paper on the teacher's desk, and from what I've read, he was a little bit of a arrogant smart aleck, so he got punished for his attitude, but he was really, he did an amazing job of recognizing the pattern and figuring that out though. So it's pretty amazing, but that's what this formula is. Notice it's the first term plus the last term, and then the number of pairs you're going to end up with is always n divided by 2. Okay? Another way of thinking about it, that at least to me is easier to remember, is this second formula in red. It's the same thing mathematically. I just took the half and I put it underneath the a sub 1 plus a sub n. Okay? To me, it's a little easier to remember because I just remember it as n times the average of the first and last terms. Okay? So the average of 1 and 100 is 50 and a half. 50 and a half times 100 is 5,050. Okay? So either way, it's the same thing mathematically, but kind of a neat formula here that we can use to figure out sums of arithmetic sequences. Okay? Alright, so that is it for today. This is not all required at the end of the notes here. If you go back to what the required IP document, that'll show you which ones are required. I focused more on ones that, take some thinking and are more application types of problems. Like this brick pattern one and a falling object, that sort of thing. It's kind of an interesting study there to look at. Okay? So, that is it.